So within the McKnight project, we are known as Research Method Support for Agroecology. And we're often asked, how is this different from research method support for agriculture? So today I'm going to focus mostly on statistics and dig into kind of two quite different case studies. Firstly, looking at an example of analysing and interpreting results from what might be considered quite a messy data analysis problem and a messy research design, and showing that considering this as a holistic approach, as a systems approach, is going to give us some much more powerful results than a traditional agricultural way of looking at the data. And then in my other case study, I'm going to be looking at how we can build up to that point and develop an analysis framework for agroecology rather than a more straightforward analysis plan for traditional agriculture. So this first example I'm going to talk through is a slightly modified and a slightly anonymized version of a project I've been working on for a number of years, which is recently finished, where the intention was to try to understand the impact of a program on quite a wide and complicated system. So this program was working with farmers in two different regions of the same country, trying to convert them from a very intensive chemical-based system of farming to organic farming. And the project was trying to provide a viable market for their organic produce by increasing the prices they could sell for to offset any reductions that came from not using chemicals for part of their production. And they were hoping this would have other effects as well beyond just the economic impact, thinking of environmental health and human health relating to not having those chemicals used in the agricultural production. And so what this program did was it had a research process involving collecting data before the organic conversion, during and after, with farmers who were involved in this process and also farmers who were not involved in this process. And this all took around 5 years worth of time from the start of collecting data at a baseline right the way through to the end. And the main question this partner were interested in was, did the conversion from the conventional production to the organic production of cotton have a positive outcome on the income and the profits that the farmers were making? And after 5 years in region 1, the result turned out very highly statistically significant. Yes, the profit of these farmers involved in the program was significantly more than the farmers who did not enroll. And in the second region, it was the same story. The profit of the farmers enrolled in the organic conversion scheme was higher than that of the farmers who did not enroll. And these two headline results made our project owner very happy as a result of putting in all this years of effort. Kind of it proved that their theory, their idea worked. So they were very happy with these headline results. But then someone came along and said, okay, but why have the profits increased? And this is where the story starts to get a bit more interesting. So in the first region, we started looking more at the data and more at some of the other things beyond just the profit. And what we could see was they were able to develop this strong market for organic produce, exactly as they were aiming to do, because they were selling for a higher price than the cotton which was produced using chemicals. But it turned out that many of the farmers were maybe finding a little loophole to exploit here, because they were still using the chemicals, but selling their crops for the organic prices. So they were getting the higher yields and the higher prices from selling, which is not something that they should have been doing. And when we looked at the other half of farmers who were following the protocols that they were supposed to be doing, they were finding that they needed a lot more labor to be able to fill those criteria for organic produce. And there was some complications here because there was a global pandemic and there was issues with hiring labor, and there were some labor shortages and labor being more expensive in this particular country compared to what the case would normally be. So they ended up having to do more labor from within the household themselves. So they were working harder, but actually paying less for labor because it wasn't available. So their expenses for labor actually went down rather than up, which helped their profit margin. And along with that, there was a higher rate of dropping out of school, lower school attendance from children who were in the sort of 14 to 16 age range, where previously there'd been quite high levels of school attendance in that range, but because they were now needed to work on the farms, this was forcing them to drop out from school or attend school less than they had done previously. So some negative unintended consequences were arising, as well as some of the positive consequences here in the first region. And then when we looked at the second region, we had kind of a different story, although with some parallels as well. We saw that there was not an organic premium for selling the organic produce in the States. Pretty much everybody sold at the same price. So their number one theory was not proved here in the second region. And actually, when we looked at the production figures, quite a lot of the organic group had reduced the amount of cotton that they were producing, because they'd seen that the yields they were getting without the chemicals were much lower, and they weren't able to sell for a higher price, so it wasn't economically viable for them. So some of them had started to diversify their crops, some of them had gone on to other things entirely. There was quite a large proportion who'd started working in construction. There was a labor shortage, so they were actually getting higher wages from construction than they might have done on the agriculture side. And then in the final year we were looking at the project, there were huge floods in this region. And around a quarter of the farmers just completely lost all of their cotton crops. And the other 3/4 had much lower yields than they would have expected to do. And it was those farmers who had reduced their cotton production who were the ones who actually did the best out of all the farmers here. Because if they diversified their crops, then they had less impact, because those crops that they were diversifying into were less affected by the flooding. And those who'd gone on to work in construction, they obviously were less affected by flooding destroying crops, because their income was not so affected by it. So they were still within that group. They were still seeing the benefits of increased profits compared to the farmers who did not convert to organic production. But whether or not this was an intended consequence and a positive consequence of the project itself is another matter. And so when we started producing the story for our project donor, they were now a little bit more confused as to the actual story, but they were more informed as to the actual story. The headline themselves, that headline of higher profit, is kind of misleading here. And that's very often the case. Your headline is not telling you the whole story. And the whole story is always going to be much more interesting and much more informative and much more useful to you as a researcher trying to generalize your findings and trying to understand the consequences of the, in this case, the conversion to organic production. We were able to tease out a lot of this story, and there's many other components of the story here. I've simplified to some of the more interesting and exciting parts. We were able to get that from thinking of the research design and making sure that we captured in the survey multiple income sources. We kind of expected that there might be diversification of crops or farmers leaving farming. We also considered that it would be relatively likely that there could be flooding events, because region 2, as I'm calling it, it was chosen to be part of the study because it was high risk of flooding. So it was known that this may be an issue that could arise. Some of what came up, we didn't think about in terms of the original design of the research, particularly thinking about the impacts of COVID on the labour market. That was not something that we were predicting prior to the start of the project, but we were able to adapt our research during the 5 years window that we had between the beginning and the end to be able to understand that better. We were able to refocus on that area and do some extra research on that area. And similarly, this idea that some of those farmers were using chemicals but still selling at organic price, that was something we didn't really expect. So we went in for more in-depth interviews with the organizations who were buying the cotton to see if this was something they were aware of, to see if this is something that maybe we need to do a bit more research to understand. Why were farmers fully understanding the implications of using chemicals in organic production? If we'd stayed with that original protocol that we had for just having some surveys at the beginning, the middle, and the end, and if we'd only focused on those headlines of what is the profit and is the profit improved, we wouldn't have learned as much as we did. If we just said we're going to do 1 or 2 single analysis models rather than breaking down everything into smaller chunks and smaller components, looking at the impacts on each of those different areas which I went through, we really wouldn't have been able to make much sense of how this all fitted together. All of these things link together. And in my next example, I'm going to kind of start from the other end of the story, start from the very beginning of the design and see how that leads into the analysis. So next, I'm going to take a quick step back and go all the way back to a very classic example of what people tend to understand as statistics for agriculture. And you can maybe see from the reference at the bottom here, we're going quite a long way back to where this example came from. This is a very classic example. I'm interested in knowing about whether fertilizer is effective in relation to some yields, in this case of sugar beet. And I'm not quite sure what combination of N, P, and K is going to do the best job of maximizing the yields. And I know that I need to have some key principles as to how I design a trial here. I'm going to go to my research station and I'm going to set aside an area of land and replicate each of my treatments. I'm going to have some different combinations of N, P, and K by themselves and together. I'm also going to have a control treatment with no fertilizer at all. And I'm going to randomize which treatment I put on which plot. And I'm going to replicate this 3 times because I'm told that N equals 3 is good as an agricultural statistician. And I'm going to have 3 different blocks, each of which contain a complete set of my treatments. And I'm going to try to control for as many possible potential sources of variation or confounding. Each of my plots is going to be managed in an identical way and be an identical size. And I'm going to try to make sure that any results I have, I can be sure that any differences are only going to be the result of the difference in the treatment, the difference in the fertilizer being applied. And so I plant my trial, I collect some data on the yield, and the first thing I do is I make a plot. And initially, I'm quite excited by looking at this plot where I can see that on the left-hand side, I'm getting lower yields from the treatments that have no phosphorus, no P. And in the right-hand side, I'm getting high yields from all of the treatments which have a P in them. The P, the PK, the PN, the MPK, all of them are getting higher yields than the treatments without the phosphorus. So just from making an initial scatter plot of my data here, I'm feeling quite excited about my results, but I know I should do a formal statistical analysis. Maybe I also want to account for the block effect. So I go and do my analysis of variance. I account for the error introduced by having 3 blocks. And I see lots of stars. I see a p-value that's 0.002. So I can quite happily conclude that there is a significant difference between my treatments. There is a significant treatment effect here, which is not particularly surprising from having looked at my plot where I have that quite clear separation. But I also think, I should do my least significant difference, my mean separation plots. So very often you'll see a plot that looks like this, where you have your letters trying to split out, okay, which treatments are significantly different from which other treatments on average. And this more or less confirms exactly what I saw from that initial plot, where all of the treatments which have a P in them, the MPK, the MP, the P, the PK, those are all significantly better than the treatments which did not have a P in them. And there's not really much difference within there, whether you have an MPK or an MP or just a P on its own. It's quite clear that what I need here to maximize my sugar beet yield is that phosphorus. And so that worked pretty well, I think, for trying to understand which of my fertilizers and which combinations of my fertilizers were doing a better job of maximizing my yield. So because it worked so well, I'm going to try and apply the same approach onto a different problem. And so now what I'm interested in is something quite different. I'm now interested in intercropping, and I want to know what happens with the production for farmers who are planting sole crop of soy, sole crop of pigeon pea, and intercrop of soy and pigeon pea. And because I want to try to understand what's happening in the real world this time, I'm thinking about what's happening with the farmers who are doing this, not just thinking about pure yields. So I'm going to recruit some farmers to take part in this trial. And because I think n equals 3 is a good number, I was told this in traditional agricultural statistics, I'm going to recruit 3 farmers to take part, and I'm going to randomize my treatments, my sole crop of soy, my sole crop of pigeon pea, and my intercrop to 3 different plots on their field. And again, I'm going to follow some of those same principles as before. I've replicated across my 3 farmers. I've randomized my treatments to each of my plots. I'm not going to control in the same way that I did last time. Planting no crop at all, I don't think makes much sense in the context of this trial, so I'm not going to have a pure control treatment. And I'm very interested in seeing what happens in the real world conditions. So I'm not going to impose some of those same management conditions that I had on the station trial. I might make some recommendations, but I'm not going to force them because I can't. It's going to be a farmer managed trial. So I go away, I let the farmers conduct the trial, and I then start to look at the results. And this time when I do my plots, I'm not quite so sure what's going on here. I've got some very different looking results from across my data here. I've got yields ranging from about 500 up to 2,000 kilograms per acre. Quite a lot of variability going on. Can't really see immediately which of those treatments looks better than the others here for yield. I can do the same analysis of variance, and I get a p-value which is 0.467. That tells me that there's no significant difference in the averages of my 3 treatments. I could do the mean separation plot, although it really is not going to tell us much because we know already that there's no evidence of treatment effects, and indeed everything gets that same letter. And I have huge, great wide confidence intervals. And in fact, for 2 of my treatments, the confidence intervals are so wide, they think there's a possibility that I might have some negative yields instead of positive yields. And this doesn't look so good. Why has this happened here? Why did we get such good results from the first case and such bad results from the second case in terms of being able to make conclusions about our treatments? And there's kind of one key thing here, which is our farmers are not the same. Our farmers can't be considered as being blocks in the same way that we have on the research trial. If we look at which farmer did which treatment, in terms of, which farmer achieved which yield in our plot here, we start to see quite clearly that, oh, farmer B is responsible for nearly all of those high values, farmer C is responsible for nearly all of those low values. We have huge differences in terms of what kind of yields can be achieved from different farms. And some things here we maybe could have controlled for. Maybe this is to do with management practices. Some were following the recommendations, some weren't. If we try to enforce something like that, then we're no longer in the real world. We want to understand what happens in the real world, not in some bubble of perfect conditions. And even if we had enforced very strict protocols on exactly how the trial was managed, there's still going to be multiple factors here which are different. There's going to be other agronomic factors, environmental factors, ecologic, maybe socioeconomic factors and demographic factors where farmer A and farmer B and farmer C are not the same. We wanted to test this in real world conditions, so we should expect to find some real world variability. It's a reality when we're dealing with research in agroecology. We're trying to understand the full system. Our classic agricultural approach is not based on farmers, it's based purely on biology. We're trying to understand the biological response of input X, in the example I gave before, different fertilizers, on outcome Y, which was, in this case, yield. And in classic agricultural statistics, it's normally yield. And we want to try to control for every possible confounding factor to be able to understand if X does Y, which fertilizer produces the best yield. That approach doesn't need a huge sample size if we're controlling for lots and lots of factors. And that's why you often see these quite small sample size recommendations of, oh, we only need 3 replicates on a research station to be able to deal with this. Kind of the reason why n equals 3 was this recommendation is because that's the theoretical minimum number of observations you need to be able to calculate a standard deviation or calculate a variance. That's not a thing which applies when we have actual large amounts of variability. We don't need to have the bare minimum to be able to calculate a variance. We need to have a little bit more data to be able to understand and really try to dig into what is causing variability and different sources of variability. I'll come on to that in a bit. When we're thinking about agroecological statistical analysis, we're trying to understand the real world system and the impact of changes on the system. So instead of just trying to understand if X does Y, we're also trying to understand how everything else, all of those things that we were controlling before, how that relates to the relationship between X and Y. And we're never going to be able to unpack all of that with just a sample size of 3. And we're also thinking in agroecology about a bit of a wider suite of things when we're talking about why. We're not just thinking about a biological response anymore. We're thinking about, yes, the yield, but we're also thinking about potential social impacts or environmental impacts or ecological impacts, and so on and so on and so on. There might be some higher end goals, but we need to try to make sure we understand the full system. It's like the example I was giving before. Yes, we can look just at the profit, but we need to understand how everything else adds up to that profit. Otherwise, we don't understand anything at all. So how can we do a better job? Well, actually, that wasn't quite a real example, the last one I just gave. In this case, this was a subset of just 3 farmers from a much larger trial. And this is one that the Best Bets project in Malawi have been working on for a few years. Kareem Longway and Wezi Mango, who have kindly allowed me to demonstrate some of the data here. And we actually had, I think, around 50 to 60 farmers to work with. So part 1 of only having 3 farmers, that was never an issue here. And we can start to look more at what happens when we analyze some of this data, but initially through that same kind of traditional mindset that we had so far, but now just with 50 farmers rather than 3 farmers. And if we're looking at our distribution of yields across our 3 treatments, when we do have a larger set of farmers, we are actually starting to see a bit of a treatment effect here. Our intercrop treatment, on average, seems to be getting slightly higher yields. And our distribution, this is shifted upwards towards the upper end. We're starting to feel a little bit more positive about our intercropping treatment in relationship with the yield compared to when we just had 3 farmers before. And we can kind of follow the same approach initially of, okay, let's now fit an analysis of variance. And our analysis of variance with 50 farmers gives us a very different looking p-value, where our p-value is now so small, it's decided not to print all the digits, but we have very, very strong evidence here of a treatment effect. And we could do that same kind of mean separation analysis here of saying, look, our intercropping treatment is significantly higher yielding on average compared to our sole crop of soy and our sole crop of pigeon pea. And there's no real difference here between our 2 sole crops. And it doesn't really matter if we're doing this analysis of variance approach that we have maybe some missing values or unequal sample sizes for different treatments, or we don't have replications on a farm level. Sometimes people get a little bit worried about analyzing more complicated data in this way, but there's nothing wrong with it at all. The methods can be almost identical. And this is giving us some information, but this is still not really telling us the full story, because we're really focusing here just on the averages. And we can even start to see this if we go back to that plot with just 3 farmers that we saw earlier. The averages really aren't telling us a story. I mentioned before we had farmer B and farmer C. Farmer B had consistently high yields, farmer C had consistently low yields. there wasn't too much difference in the yields across the 3 treatments for those 2 farmers. I kind of intentionally ignored the most interesting farmer there, who's farmer A. And this is a farmer who got very low yields for the 2 sole crop treatments, but got a really high yield for the intercrop treatment. And so rather than trying to understand overall, is there a difference on average, which if we apply to our 3 farmers, yes, there's a difference on average, but it's only 1 out of our 3 farmers who really sees that difference. The other 2 doesn't really see that difference at all. So what we might want to try to do is understand, okay, who are farmers like farmer A? Who are the farmers who could really benefit their yields from moving to an intercrop treatment? And who are the farmers like farmer B who are getting consistently high yields? And who are the farmers like farmer C who are getting consistently low yields? That's what's going to tell us some really useful information and really actionable results here. If we just find out that the intercrop treatment is better on average and then apply it all around, that's not going to be as useful, or not going to tell us as much as if we can really understand what are the factors associated with high performance of the intercropping treatment. So maybe let's dig into this a little bit more. What factors might theoretically be associated with a high performance of the intercropping treatment? And actually, I missed a little bit when I was explaining the setup of the trial here, because there were 3 different locations where the farmers were taken from, 3 different villages. And if we do our exploratory analysis here by location 1, 2, 3, something immediately jumps off the page, where in location 2, our intercropping treatment is really outperforming the 2 sole crop treatments by a large amount. Location 1 and location 3, if we look a little bit more closely here at the distributions, we can see the intercrop treatment doing a little bit better than the 2 sole crop treatments. But in comparison to location 2, where we have that really, really strong treatment effect, then yeah, we've got a very different situation here in the 3 locations. This is the kind of thing we might have considered, oh, it's a G by E interaction, a genotype by environment interaction. Although in this case, we're thinking of different intercropping patterns. So maybe it's a O by C, an option by context, as we used the terminology a few years ago. But just knowing our 3 locations here, that's not really telling us so much. It's not really so generalizable. What is it about location 2 that means the intercropping treatment is performing better? Is it to do with the soil or the altitude, or the farmers managing their plots in different ways, or there's just a different attitude towards intercropping there? It's something they've done for many years in that location, where it's something new in the other 2 locations. There could be any number of factors related to location 2, which help to explain why the intercropping treatment is better. And the better that we can understand those factors, then the better we can generalize our findings and be able to make better conclusions about our interventions and our treatments, and understanding that whole system better. So we might start thinking about this in our research design and start factoring in, okay, let's try to work in locations which are very different from each other, and there are different factors in our different locations to try and understand, so that we have this comparison rather than working with multiple different locations. But let's also make sure we collect data about those differences, rather than just saying, okay, we're in these 3 locations and we'll put this as a factor in our model. If we keep doing some more exploratory analysis here, something they did very well in the Best Bets project was they collected lots of data about the locations alongside it. So we had the clay content in the soil, as well as other soil parameters. But it was a clay content that really jumped out when I was exploring this data. We can see in location 2, much higher clay content in soil than locations 1 and location 3. So maybe this is starting to explain some of this effect. And then if we get even more specific and start looking, okay, within location 1 and location 3, as we increase the amount of clay in soil, the farmers with more clay in their soil in those 2 locations, those were the farmers who were getting higher intercropping yields in relation to the sole crop yields. and it was the farmers with the lower clay content where everybody was getting more or less the same kind of yield across the three treatments, and in some cases better yields from the soil crop than the intercrop. Didn't quite work out as neatly as it could have done, because we can see back in location 2, where we had the higher clay content, yes, on average, the clay content was higher, but there was a relatively flat line here as I try to fit my line here. So generally within location 2, there must have been other factors as well beyond the clay content here, which helps explain why some of those farmers were getting higher yields. Even those farmers with lower clay content in location 2 were still achieving better intercrop performance. So we need to try to think about, okay, what other factors do we think might be important here? And so this is a point where we maybe need to take a step back and try to build up our theoretical framework of how it all fits together. And we can start to do this generally in very general terms before we even think about collecting any data. This is going to be really informative for how we choose to design our research. We don't need to know anything about the research methods or the statistics at this point. We just need to think about our scientific theory and the context in which we're working in. So we might start with a point of knowing that our different soil characteristics, some of them may be better suited to intercropping and may result in higher yields from intercropping under certain soil properties. And we also know that, okay, we might have different land management practices, which might be better suited to intercropping. But those land management practices, those also may link into the soil characteristics, where different management practices are probably going to be better for the soil than others. And on top of that, we might start thinking, okay, but there's a demographic factor here as well. It may be the case that wealthier households are going to have better access to high quality land. And there may be gender components in terms of female farmers may have less time available for working on more labor intensive land management practices. This is not meant to be a complete process here. When we would go through this for real, this is the kind of thing we might need to spend quite a lot of time working out how we're mapping things together. We often think of theories of change and things like this when we think of our overall project input. It's quite a similar idea here, where we're trying to understand a system and we're trying to understand the different components of the system. And there will be relationships between all of our different components. It's not as straightforward as everything links into yield at the end. Different things link in different ways. And our traditional agricultural approach, again, is just thinking about maximizing that yield. But within agroecology, we're thinking of multiple outcomes here. It may be that our intercropping ideally is going to be resulting in perhaps better food security and nutrition, because we're having more nutritionally diverse crops being produced, increased quantities of food able to be stored. And there may be relationships here between our results and between our outcomes. If we have better food security, this will lead perhaps to better nutrition. And we want to try to make sure we capture these results. And it may be things that we were thinking about as predictor variables, thinking of explanatory variables. These may turn later into outcome variables. If we think about our soil health, one of the reasons that we like to do intercropping in the first place is it may provide better nutrients back to the soil. So the soil itself may improve through longer term intercropping. And so our system can double back on itself. We need to try to understand how these variables link to each other and how these properties link to each other. Once we've worked on our general process here, our general influence diagram, this is the point where we can start trying to work out how we can understand and quantify or qualify or better research each of these different relationships and each of these different components. So instead of having quite general boxes here on our, what we might call our influence diagram, as one of my colleagues likes to call them, we might start converting some of these into things that we can actually measure or understand a little bit better. So instead of thinking of soil characteristics in general, we might start thinking, okay, this means clay content, or this means a subjective assessment of the soil quality. And so we'll start to think about how we can measure each of those different components. And it may be the case that some of these are things which could be measured immediately. So things like trying to understand the relationship between demographic factors and management practices and soil practices, soil quality. This is the sort of thing that you could understand quite well from doing a wide baseline survey in the area that you're working with. Other things like trying to understand the impact of intercropping, that might need a more designed trial, like the thing that we've been describing so far, that with the Best Bet project we're working on, because we'll need to understand, okay, what happens under intercropping, what happens not under intercropping. So there we might be thinking about designing an experiment. If we're thinking about some of these longer term impacts, the adoption of the intercrop, and whether this improves nutrition and food security and other factors, that's something which would again need a slightly different research design to try to capture, because that needs to be looking at a longer term outcome rather than something that we can measure in the space of 1 season or 2 seasons worth of trials. So we have our general diagram, but within this diagram, we might need to be breaking it up into different components for different research activities. There's a temptation when you see a diagram like that to jump to a very sophisticated type of statistical analysis. So there's a relatively well-known approach called structural equation modeling, which deals with all these pathways between variables, and they can double back on itself, and it tries to capture that whole system. But there are some limitations to that approach. And in particular, it's kind of assuming through that approach that you have the whole system being captured. And as I said, some of these different pathways might be capturable at different times. There may be limitations of time and scale and different levels being involved as to whether we can try and model that whole system all in one go. We might have multiple different things to consider. So the rainfall, for example, might vary from village to village, whereas our land management practices, that might vary from farm to farm, and our soil composition, that might vary from plot to plot. We can have very different soil from even on the same farm, from one area of the farm to another farm. So these sophisticated modeling techniques have their place, but often we don't really need to go through them to understand the full system. Multiple sets of models which fit into that framework and are coherently formed in a way that makes sense and in a way where they are statistically valid, unlike some of the other cases I went through earlier. They will be not only able to do the same job, they'll probably be able to do a better job. And you'll be able to construct them in a slightly easier way, because these are going to be more straightforward statistical models. These are pretty much going to be just a regression model, maybe a logistic regression model, rather than a more black box type of approach through some of these more complex statistical analyses. The other thing to consider as well is that with that approach of trying to model the whole system, that's assuming that everything here can be quantified, and all important knowledge is quantifiable and modelable in a statistical analysis. And there's always going to be some very key relationships and key things here where perhaps the best way of understanding that is not through a survey or an experiment. It's something that we might need to have a more qualitative approach. We might need to really start talking to the farmers and really start understanding some of these relationships through a more qualitative lens to be able to understand the full system. And that's a real strength of this approach of having our influence diagram, that we can break it up and break it down into multiple types of analysis, not just multiple statistical analysis. We can have all sorts of different research activities which link in to our overall model. And that's exactly the approach that we took in the first example that I gave earlier, where we had different kinds of surveys, and economic data alongside interviews with farmers and alongside interviews with people working in the markets to try to understand that full system. So I'm going to now go back to my influence diagram here from the Best Bets project and dig into some of these relationship pathways and use this diagram as an analysis plan for how I can try to understand what's happening within this wider system. And so one of the outcomes that we do have here is yield. Again, I'm going to acknowledge that there are other variables I'm likely to be interested in for a wider analysis of this data. And I'm going to resist the temptation to try and fit everything, all of my variables, and see what relates to yield, and just focus on those which I think are important from the context that I'm aware of and from the scientific theory. So here, all I would perhaps need to do in this case, if I've designed the data appropriately to collect those pieces of information in an easily quantifiable way, I can do a multiple regression model here of fertilizer time and clay content in the soil, and a subjective assessment of the soil quality and the planting time. And we can see which of these variables may or may not be significantly associated with the yield. In this particular case, when we're thinking about the yield of the intercrop being better than the yield of the sole crop treatment, we don't see an effect particularly of the soil quality or the planting time, but we do see an impact of the fertilizer time and the clay content in the soil. Our influence diagram might be a living document. As we start to learn more about the system, we can go back, we can refine it. The fact that there's no significant relationship in our data doesn't mean those factors can completely be ignored, but we start to get a better picture of which of the variables we do have evidence for having a strong relationship with our outcomes. And we can do this from multiple different parts of the influence diagram, trying to understand multiple different parts of the system. Maybe we move back a step to thinking about, okay, which are the factors related to that soil quality? And this time, instead of looking at some of the more agronomic factors, we're also bringing in some of the demographic factors to do with education and gender of the farmer. And one thing from this Best Bets data that really jumped out was how the soil quality varied by the gender of the farmer. We could see that 57% of the female farmers had what they considered to be poor quality soil, and it was only 27% of the male farmers. And only 4% of the female farmers had good soil, compared to only 27% of the male farmers. So this was a factor which would be really interesting to try to dig into more. And again, it's a little bit like location when we saw before. It's not purely because they are female that their soil is poor. We need to try to understand what it is here about this relationship which results in female farmers having poor soil quality. And I think this is a very good example of the sort of relationship here, which is going to be much better understood through a more qualitative lens than a quantitative lens. We can try to hypothesize and come up with which variables may be statistically related to this pattern, but actually getting on the ground and speaking to and observing some of these situations is going to give us a much better understanding of the gender dynamics and how that links to the quality of land that they have available for production. So we need to try to understand our full system as best as we possibly can, and that's going to come through doing multiple research approaches and multiple models, rather than doing very simplistic models or very overcomplicated models. The main thing that I wanted to try to capture in this presentation was to emphasize the difference here between the classic agricultural approach to statistical analysis, which is almost entirely focused on picking out the headlines of is yield better under certain treatments. With the agroecological approach, yes, we may still want to look at those headlines, but our focus should be on the story. why are we seeing differences? And to be able to do that, we need to try to understand the full system. And this requires us to break that down into the different components of the system and try to understand the relationships within there. And that may involve an approach which actually uses a lot of the same statistical methods as classic agriculture. We still may be doing exploratory plots with scatter plots and bar charts and box plots, and we still may be looking at linear models and analyses of variance, but how we apply them and how we interpret them may be slightly different. We're having a different way of approaching the same sort of methods. And there may be other methods as well that we bring in. We bring in not just our statistical analyses, we need to recognize the importance of other sources of knowledge and other sources of research information beyond things which can be purely quantifiable and modeled statistically. And all of this requires much more conscious thought and planning throughout the entire stage. With our classic agricultural approach, we more or less do the same thing, just with a different set of treatments and a different set of crops, and we'll have our different kinds of blocks to design, but ultimately, more or less everything is perhaps the same. Whereas with a more agroecological project, we really need to adapt our data collection, adapt our research design, and therefore adapt our analysis approach to the specific context in which we're working. And to be able to do that well, we need to have a process which involves not just people who do research methods or statisticians. We need to be working very closely together with the researchers, the scientists, those of us who like doing the research methods, and also the farmers themselves, so that we're really trying to do the best job we possibly can of understanding the full story of the agroecological system that we're interested in researching.